Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, my name is John Nordlinger. I'm with Microsoft Research, and I'm very pleased to introduce Ian Horsweiler from Northwestern University. Ian comes from a long time ago from the AI lab at MIT. He now is at Northwestern, where he's the director of the Animate Arts program, a nice blend of computer science and art to produce great objects like the one he'll be talking about. He also is a professor, and he teaches computer science at Northwestern. Please welcome Ian Horsweiler.
Thanks, John. Okay, so let me just start out by asking how many people here come from kind of an AI research background? Okay, how many people come from a game design background? Okay, and any other kinds of backgrounds here? Like, okay. Education. Oh, okay. All right. So I'm going to try and cover a few different topics. And so I come from a tradition that believes in interactive talks. So if you have a question, please don't feel bashful about asking it immediately, and we can talk about it some more. Especially since there are a few different topics I'm supposed to cover, I'm going to be going somewhat quickly through some things. So this is in some ways less a research talk. This is about a tool for procedural animation that I made for my friends and me in interactive narrative research, so that we would have sort of some nice bodies that we could use as backends for our AI systems. I'll talk mostly about the system. I'll also talk somewhat about sort of the longer term goals. Why do we need this tool? But I want to start out with just a quick demo. And hopefully none of you know about Ainsworth's safe home base phenomenon. Okay. Sorry, I'm having a multiple screen issue here. There we go. Oh, thank you, sir. May I have another? All right, just one moment. I can just run the silly thing manually. Okay, here we go. And so I'm going to deliberately not tell you too much about what's going on here, other than to say that this is all sort of being computed from first principles. So, I never learned to use Maya. I didn't make a walk loop for this or anything like that.
The same every time you run it? Or?
No.
So this could be a good example of that.
Okay. So that's an example of, sorry, I need to, here we go, of an application built with the system. It's trying to test out, trying to do a simulation of some specific results from what's called attachment theory. But, okay, All right, so now I want to ask you, what did the kid character want? Or in general, what can you tell me about what was going on in the heads of the characters? Sure.
He wanted his parent, it seemed like.
Okay. Anything else?
He wanted the ball.
Okay. Anything else? You pretty much have it.
He wanted to play.
Yeah, wanted to play. Is it also has a somewhat anxious relationship to the other kid. So you didn't really see it, but sometimes, you know, he would like punch the other kid. Okay, so what I want you to get from that, so, you know, that from an AI standpoint, that was a really simple demo. It was if you know about behavior-based robotics, it's a straightforward, pretty simple behavior-based control system. But it's interesting how, even though there was no language there, there weren't even any facial expressions, you could learn a fair amount about what the characters were involved in, you know, what they wanted, what the conflicts were in what they wanted, and so on, by things like bodily postures, by pauses and hesitations, you know, the kid's chasing the ball but periodically stops and looks back at the parent, or when it's running toward the parent, it stops and looks back at the ball, gaze direction, and so forth. Okay. So, although I'm an AI person, and I'm interested these days particularly in simulating emotion and personality, I'm interested in doing that in the context of interactive drama, so virtual characters for interactive drama. And so what I personally really want to do is I'm interested in making characters that feel compelling as characters. A lot of other problems to work on, like making the characters really smart, having really good drama management to manage the Aristotelian arc of the story and all of that. That's not what I'm working on. I'm trying to make characters that seem kind of lifelike. And so, as I said, I'm sort of hanging out with friends from the psychology department and neuroscience and so on. In order to do that, I needed to build some bodies, and that's largely what I'm here to talk about. But just in terms of background, what I'm interested in thinking about are kinds of games in which the players are really going to them to have some sense of connection to a character. That's one of their primary motivations. So not just challenge, but actually to have some sense of connection to the characters. And there's actually quite a long history of this. So Tamagotchi, for example, you know, people who like Tamagotchi like them because they're a kind of child and they have an attachment to them. Or, you know, the old Dogs work by Andrew Stern, Nintendogs now, and now Andrew's doing Touch Pets dogs. That's what that's a screenshot from. But there's also interactive fiction, visual novels. How many people know what visual novels are? So they're a kind of interactive fiction that's very popular in Japan, which is basically static graphics with text. And it's very much like a choose-your-own-adventure novel in that you're moving through dialogue trees and choosing discrete moves. But it's really very minimal. It's, you know, static images and just text. And yet they're enormously popular in Japan. At least as of 2006, they were responsible for 70% of the titles, PC titles, that were released. So there are things like this. You have a picture of a character, you have the dialogue you're having with them. The dialogue you're having with them is fixed choices, but these things are incredibly popular. Okay, so that's where I'm coming from. That's the kind of project I'm involved in. I want to think about how do we make characters that feel engaging, AI-based characters. Now, when I started getting involved in the interactive narrative world, one of the problems I had was that I couldn't find sort of a good game engine to use. And in fact, a lot of my friends were very frustrated by 3D and thinking about going back to 2D. As my friend Michael Matias said, what we really needed was procedural South Park. We needed sort of flat, simple stuff, didn't need a complex world, but needed a world in which it was easy to just introduce a new prop into the world and have the character interact with it. And if you needed to add a chair to the world, it didn't require that you hire an animator to animate the sit-down animation, because the chair has a slightly different height than the chair that you already had a sit-down animation for. Okay, so that's what the bulk of the talk is going to be about. And then time permitting, I'll also give kind of a flavor of the work that I'm doing with my friends in psychology these days. So here's the real problem. How do we make flexible animation backends that are easy to interface to your AI system, in part so that my colleagues at Northwestern stop asking me if I can recommend students who know Maya who can do their animation and modeling for them. So we're looking to build a system that has a pretty wide behavioral repertoire, that's easy to interface to the AI system, that can provide some reasonable amount of physical interaction between the students. So you saw the child character physically hugging the parent, and you want to be able to do that kind of thing. And you want it to be relatively easy to add props to the system. You want at least sort of cartoon level believability. So the gold standard for that kind of animation is, of course, hand animation, and motion capture gives you very, very, very nice results. It's infinitely tweakable and so on. As you know, it's expensive. It's also, for a lot of us in the university setting, just prohibitively expensive. We don't have a motion capture studio at Northwestern. There are actually very few students who have the facility with Maya to do real character animation, because there aren't any courses in it. So a really attractive alternative is to do some kind of full-blown dynamic simulation of the body, run an inverted pendulum controller in the body to keep the body erect, and then generate the walk loop that way. There's been a lot of really great work on that. It's still fairly expensive computationally, and it's also expensive in terms of development, in that you need separate controllers for the different kinds of actions. You have to worry about stability issues. The controllers themselves may be relatively unstable. Physics can sometimes be unstable. And plus you have to worry about the fact that even if you have a walking system that works for the character under normal conditions, if they're walking with a load, now you actually need a different set of gains in order to keep the walking system stable, and so on. Okay. There's also been a lot of wonderful work on data-driven methods, where you just go and grab a whole lot of mocap and you either cut it up into little pieces and dynamically sequence them, or you use them to train a dynamic controller. Just use it as the training data for the dynamic controller. You get pretty good realism. It's still not really appropriate, at least for my kind of environment, because we don't have the mocap data to begin with. And then if you're trying to fit it onto a console, it is a fair amount of data that you have to keep track of. So I just built a system for myself called Twig, which does sort of rough and ready procedural animation in a dynamic environment. And now I have a lot of friends who want to use it, so I'm trying to package it up so that it's usable by other people. But really what it's trying to be is just a pragmatic tool for procedural animation that you can use as a backend to your AI system. So I'm not claiming to have made any innovations in physics simulation or control theory or anything like that. It supports some amount of dynamic simulation. It's not great dynamic simulation, but it works fine as far as the audience is concerned. And it's intended for sort of interactive narrative applications. So I want it to be fast. I don't want you to have a separate CPU to run it on. I want it to be easy to interface the AI system to. I want it to be easy to run it over an RPC link if you want to hook it up to something like SOAR, which is running in a separate address space. And I'm more interested in believability in the Joe Bates and Disney animation sense than in actual physical realism. So as long as it's emotionally believable, I don't care whether or not it's physically realistic. So it's free. It's a XNA library. You can download it. It integrates with the content pipeline, which is awesome. Not its integration with the content pipeline, but the content pipeline itself is awesome. And once I find the right undergraduate to work on it, we're going to port it to the Xbox. The main idea behind it is a kind of a puppetry style of control that I'll talk more about in a minute. The basic idea is it's fast and stable. It's relatively easy for people who don't have too much specialized knowledge to go and extend, or at least that's my sense. I haven't done other people haven't written code for it yet. And it's very much a work in progress. This is my second 3D graphics program, so I'm sure you could all do it much better than I did. But, it's academic research code, sorry. Okay, so here's what I mean by the puppetry control style. Essentially, what you have is a puppet. You have a ragdoll simulation, and then rather than trying to do inverted pendulum control or something like that, the way you're going to do control is you're just going to apply forces directly to whatever parts of the body you want to. Essentially, if you want the character to stand up, we give you a jetpack. You can attach the jetpack to the back of the neck and have the jetpack lift the body up and center it over the feet, and that's how you do standing. If you want the character to stand and also wave its hand, you have one jetpack here, you have one jetpack here. They're both flying around, and then the physics system is going to worry about where the other parts of the body go subject to the constraints of the forces that are applied to the relevant parts of the body. Make sense? Okay. The physics system is based on Jacobson's, I don't know how you pronounce this, his name, work from the Hitman engine. Fantastic paper from GDC 2001. Basic idea is you model the body as a set of point masses, i.e. particles, connected by rigid distance constraints, i.e. massless rods. And you use Verlet integration to update the positions of things. Verlet integration just means that you model the state of the particle in terms of its position in two consecutive frames rather than in terms of position and velocity or position and momentum. The thing that's nice about that is that it makes it easy to do constraint satisfaction, because if you find that a particle is a place it shouldn't be, you just figure out a better place for it to be and then you move it, and you don't worry too much about updating the momentum. You just move the stupid particle and you hope it looks good, and mostly it does. Okay? Fair enough? All right. So for example, so you're updating say you have two particles that are connected by a rigid distance constraint. You let them move however they want to, and then once every clock tick, you say they're supposed to be this distance apart. They're actually this distance apart. So we move them to the places where they need to be. How do we know what that is? Well, we do the thing you would normally do, which is to pretend that they're connected by a spring, but then you just solve for what the rest state of the spring would be, and you move both particles there immediately. So you're doing constraint satisfaction by projection. Okay. Given that, you can now, so now you have a character. You have everything you need to do to hook a bunch of particles together in a kinematic chain by way of massless rods, so you can make a ragdoll body. And that's basically how the ragdoll for Hitman is done. And now what you can do is if you want to move the arm someplace, you just grab the particle for the arm and you move it wherever you want to move it to. And the constraint satisfaction system is going to make sure that the elbow is someplace that's compatible with the position of the hand and the position of the shoulder. And if there is no such place, then it's going to drag the shoulder along with the elbow. And then when you stop dragging the hand, everything's going to behave as if it has normal dynamics. Okay? Now, the thing that's nice for my kinds of applications are that when people want to go and build a system that uses this, they don't have to think about joint angles. They don't have to think about dynamics. All they have to do is figure out what linear forces do I want to apply to the particular parts of the body that I care about, or even just teleport the parts of the body that I care about to the places that they need to go. And I don't have to know, I don't have to think deeply about physics or kinematics or anything like that. I can just grab parts of the body and move them where I want them to go. Posture control works in pretty much the same way. We essentially attach a bunch of jet packs that are doing little servo loops to different parts of the body. We have a jet pack in the middle of the pelvis, which is holding it at the right height and centering it over the midpoint of the feet. We have another one that's centering the top of the spine over the midpoint of the pelvis, subject to the constraint that we want to balance out the center of mass. Then we have separate things that are applying torques to the shoulders to make the body face whatever direction I want it to, and independently to the pelvis to make it face whatever direction we want it. Okay? Any questions? Yeah?
So it sounds like you've got a combination of these jet packs, or as an alternative, you have like position-based, like keyframe-based?
Right. So for things like if you want to animate a hand wave gesture, might as well just do that through keyframe. And so yeah, and in fact that's the major thing, other than importing prop models, that's the major thing we use the content pipeline for, is you can make little XML files that describe the keyframes for I want the hand here, I want the hand here, I want the hand here, and how fast do I want it to move, and things like that. So yeah, you can do keyframing, but for posture control, the walk loop and so on, you don't have to.
So you can mix them?
Absolutely.
So how do you keep the elbow inverted?
Oh, great question. Sorry. Yes, so implementing joint limits is a pain, and pretty much you do it. Actually, so truth in advertising, the elbows are the part that's a pain in the butt. The knees are easy because you just figure out what plane do you want the leg to lie in, and then you just enforce the constraint that all the nodes of the leg need to be coplanar in that plane. And so if you want the leg to be facing this way and the knees out a little bit, you just move the knee in toward that, you move the other nodes a little bit the other way so that you conserve momentum, and that holds the knees in place in whatever direction you want. For the elbow, you do the same thing, but it doesn't look as nice because, well, what you want is you want sort of a smarter system deciding what plane it wants the elbow to be in, and right now the system that's figuring that out is dumb. Right. So, I actually don't remember how it decides what plane it should be in, but at the moment it's doing something stupid because the stupid thing works for what I've had to do so far. Anything else? Great questions. Okay. So there's posture control. So yeah, we just basically as it were, apply jetpacks to different parts of the body. We control the parts of the body we care about to do the things we want to do, and we control them independently. Parts of the body we don't care about, we just allow to move freely, and then physics takes care of resolving the constraints between those different bits of control. And so the control system then ends up looking like sort of a typical behavior-based system. Essentially, you have a bunch of very simple servo loops that are all running in parallel and to varying degrees communicating with one another. And I'm going to talk about that in more detail if you want to, but there isn't much that's too interesting to say about it. Gait generation is based on the more recent work of Ken Perlin that he hasn't published, but the trick is just translate the pelvis along the trajectory that you want it to go on, and notice when one of the legs is stretched out behind you. When the leg is stretched, keeping the feet planted. When one of the legs becomes overly stretched, just move it ahead of you along the trajectory you want to move in, and that's enough. So Ken did that with a kinematic solution in explicit IK. I'm just basically ripping off that idea and doing it in this, sort of quasi dynamic simulation. Okay.
Do you have a problem with stability in the sense that you're enforcing multiple constraints and there's some sort of cycle and the thing just won't stay still? Or do you just damp it?
There is damping. In practice, the only time you really get oscillation in the bodies is when you really ask them to do something that's impossible, such as when the character is picking up an object and you ask it to move the object through the body, that kind of thing. But there isn't a lot of oscillation. There's more oscillation actually at the higher behavioral levels, where you get like thrashing, where the system wants to follow the ball, no, it wants to go to the parent, wants to follow the ball, no, it wants to go to the parent. But I don't want to oversell this. So no, I don't get a lot of oscillation, but it's not that I'm getting stability because of my awesome integrator or my awesome insight into gait generation. I'm not getting oscillation because I'm asking the system to do something that's really pretty simple. And so, in practice, I haven't had oscillation problems so far, at least.
When the character's standing, you're enforcing a couple constraints on the feet, right? Which you're going to potentially. I mean, when your character's just walking around or jumping or that sort of thing, I can understand that you have essentially a hierarchy of
Mm-hmm.
Can't call them joint constraints or something else.
Right.
Distant constraints. But now, as soon as you put both feet firmly planted on the floor, then you have a cycle. Right? It's not
Well, except the constraints are being implemented at the feet and at the pelvis. The knees are being constrained in one degree of freedom, but then there's still a spare degree of freedom so that the knees can bend.
Okay, so you're solving for the legs and the feet and the torso all at once.
Well, right, except the trick is I don't actually need to solve for the position of the knees. I just move the pelvis where I want it, the feet are where they are. And so if when the character stands up, for example, let's say it's starting from this position. I want it to be in this position. I just start the jetpack on the pelvis. The pelvis starts rising, and then the distance constraint on the knees pulls the knees in. So I don't actually have to explicitly compute the IK for that. It's being implicitly computed.
Okay, I can see how damping would be pretty important in this system.
Yeah, I mean, there certainly is a lot of damping in it. You know, and I could try turning the damping off. There's a lot of damping in it, not so much because I saw a lot of, at least I don't remember seeing a lot of oscillation in it, but what you get is, you know, the character, you know, when the character runs into something, it restores from that too quickly. And so you want damping just so that it's acting like a body that has some viscous damping in it. And so there's a couple of different flavors of damping in it. There's damping relative to the environment frame and then damping relative to the body frame, which gives you a sort of kludgy approximation to the kind of viscous damping you get in the musculoskeletal system. You know, all I care about is that it looks good enough so that I'm not embarrassed by it, and then I can move on and work on my AI. Okay, anything else? All right. Then the other thing you want, of course, are props. And so the easy part is it's built on XNA, so you can just use the content pipeline to pull in any old model you want. So that part's really easy. The harder part is that, at least in the current system, if you want a better collision proxy for it than its bounding box, then you actually need to write some C# code. And there's a specific set of collision volumes that it understands. So they're the standard boxes and capsules and spheres. And also, if you want the user to be able to interact with the object other than by bumping into it, then you need to write some C# code for to tell the system how to manipulate it. So the way that object manipulation works is, if you want the character to be able to interact with some tool object, for example, so, you know, say I want to be holding the clicker in a particular canonical position, it just turns out the easiest way to structure that is to put the knowledge of it inside the class for the clicker rather than inside the class for the character, so that we don't have to keep adding methods to the character class all the time. And so the way it actually works is the clicker figures out where it should be in space, and it hovers there, and it drags the character's arm along with it. And actually, that's one place where, if you're not careful, you get oscillation, which is that the clicker is figuring out where it should be by coming up with a post hoc bodily coordinate system for the character based on where the shoulders are and so on. And so it figures out, I want to be there. And if the body isn't running a control loop that's trying to keep it facing in a certain direction, then the fact that it's reaching forward is going to drag the shoulder forward a little bit. And so now that coordinate system is slightly different. And so on the next frame, the target position for the clicker is a little different. And so it drags and so you get this very slow precession if you're not careful. So that is one case of oscillation, although not in the usual sense we think of in control theory. Okay? Fair enough? So the way that, for example, a character writes on a clipboard is the clipboard asks the body for its coordinate system, figures out where it should be in a coordinate system that's normalized to torso size and arm length, and computes from that 3-space position, and it goes and hovers there, dragging one arm with it. The pen asks the clipboard where its writing surface is and asks for the global position and orientation of a particular position on its writing surface. The pen moves to that position and drags the other arm with it. And then writing is just the pen moves around within the coordinate system of the writing surface. Now it's not, it's not super realistic, it's not dynamically accurate, but it's very convenient. It's just much easier to build the system, and it looks good enough. One of the things you end up wanting to do is to have sort of a lot of task-specific coordinate systems, so there's a system for that so that objects can tell you what their front surfaces are or what their writing surfaces are and things like that. So here are the kinds of things that you can do at the moment in Twig. You can hold an object, which means one of the hands is attached to it, and then it's just hanging at the side of the character. Hold for use means move me into whatever my canonical position for utilization is. Obviously, that'll need to get generalized at some point, but for the moment, it's good enough. Pen writing on a surface, walking, sitting, standing up, playing a gesture file, approaching an object, attacking an object, attachment, which is the kid running up and hugging the legs of the parent. There's a pain withdrawal reflex, so if you hit one of the characters, there's a low-level reflex that just overrides everything else and does an undirected escape response for a short period of time. Gaze control, speech balloons, so to speak. Oh, actually I have to sit down and stand up twice. Sorry about that. There's a sensing system built in. You have tactile sensing, so you know when something touches you and what body part, and you know what object touched you. You have nociception, which is a fancy way of saying pain sensation. So if something hits you hard enough, i.e. the kinetic energy is over some threshold, then that also gets registered. Characters scan their field of view. There will be auditory perception, but there isn't right now. Okay? A lot of the users of the system, so from this point on, we're talking about the AI system that Ian wants to use, which a lot of my users ignore because they just go in through the remote procedure call interface and bypass all of this and just say, move the hand, walk over here, and so on. But there's also a autonomous attention system that's appraising the salience of objects in the environment, moving the focus of attention around. There's a short-term memory that's tracking that. There's a gaze control system that's semi-independent of that. It tries to mostly pay attention to the focus of attention, but it doesn't always. And in particular, it's trying to monitor, balance its attention between different objects that need to be monitored. There's, for those people who don't want to write C# code, I actually like writing C# code, but for those who don't want to, you can just hook up to it over a TCP port and spit commands at it. Yeah, camera control. Yes, there is a dumb camera system in there right now. Arnav Jalla, who had been at Copenhagen and is going to, or is now at Santa Cruz. He did a thesis in Michael Young's group on camera control, and he's got students working on doing smarter camera controllers for Twig. But at the moment, what you've got is, point the camera at this object, set my field of view, set my distance, set my height, that kind of thing. But yeah, you definitely want something smarter than that, and ideally, you also want to be able to reason about, I want a two-shot with, this character larger in the screen than that, and, make sure that everything you want to be in view is in view and stuff like that. But
seems like you ought to use the behavior system itself for the camera as well.
yeah. Well, that would certainly be what I would do. Most of my friends who want to use this want to use their own AI systems, though. So, I happen to come from the behavior-based tradition, and I kind of think that way. Most of my friends come from, a reactive planning tradition, so they want to have that kind of thing. And, I'm trying to minimize my barriers to entry, so to speak.
You mentioned possible collaboration with SOAR. You talking to John Laird about doing that?
Yeah. Well, if by talking to, I mean I shot John a note saying, John, how do I find out about the foreign function interface for SOAR? And John says, great, here's the documentation. This would be really cool. And here's the name of somebody to talk to. Now, have I actually had time to build the foreign function interface? No, but that's on the queue. Okay, well, now let's see whether we can launch this one or whether I have to launch this one manually also. I can launch this one. But it's popping up on the wrong screen. Okay, so this is an example of the scripting interface, which is sort of the prototype for the RPC system. And so I was doing a kind of a webcomic, so to speak, with it. Okay, so that's an example of controlling it just by saying do this, do this, do this, do this. In this case, from a text file, but you can send the same command set over a TCP link. And just to give you a sense, this is what the code looks like. I mean, it's just the obvious stupid thing. You have one line per command, and it's just method calls. This is the name of the object. You look it up in a table. This is the name of the method. You use reflection. You parse the arguments. You call the method. You're done. So nothing terribly fancy here. But you can, Michael says to Brian, and you give a string for the thing to generate in the dialogue balloon. And so Michael knows then to turn toward Brian because he's addressing Brian. Brian knows to shut up until the word balloon disappears, and then Brian goes and picks it up, blah, 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 blah. Okay, any questions? Yeah?
Do you have sort of a lightweight physics system built into this, and is there a way to give objects weight?
Yeah, so the lightweight physics system is the particle stuff. And so, for example, I mean, it's kind of, I'm not a physics hacker, so the way this is modeled is I just have a cube made out of 8 particles with distance constraint, invisible rods linking them together into a rigid structure, and then I set the weights of those 8 particles to be very large so as to simulate a 16-ton weight. I'm sure that,
So you have gravity.
Yeah, absolutely, yeah. So you have dynamics in the sense that there's gravity, objects have momentum, there's, a little bit of damping and stuff like that. So it is a dynamic simulation, but it's a dumb dynamic simulation, so don't expect too much out of it. And also, the procedural animation system violently contradicts conservation of momentum and energy. So remember how I said gait generation gets done. We put a jetpack on the pelvis and we push it forward. Well, that means, you may not have noticed it, but in some of the scenes there's a merry-go-round that the kids are running around. The merry-go-round actually works. You can get on it and push it and it spins and all that. But if the kids get on the merry-go-round, since their locomotion is being done by an external force that's pushing them, they could actually push the merry-go-round while they're walking on it, which isn't physically possible in the real world. Now, in practice, they don't try to do that, so it's not a problem, and so I haven't tried to fix it. But, there's trying to be enough physics so that it doesn't look stupid. but not so much physics that I have to think deeply about physics. Blah, blah, blah. Okay. So that's the Twig system. What's it bad at? Accurate simulation. It's not trying to be an accurate simulator. It's trying to be sort of a cartoon simulator. Cartoon physics, cartoon rendering. I mean, not in the sense of cell shading, but it's stick figures, folks. So it's not good at photorealism. Collision detection is very simple. There's no path planning in it. It's potential fields. But what it's good at is sort of, it's a rough and ready system where if you want to introduce a new kind of object, you have some hope that an undergrad who knows C# and hasn't taken a lot of graphics classes or AI classes or robotics classes can go and write the prim-op for that. Because of the little bit of dynamics you have in it, it does produce, to my eye at least, relatively expressive motion. I mean, the motions I think are relatively pleasing. Your mileage may vary. But the idea is to get believability in the Disney sense. We're not trying to get realism. We're trying to get something where you look at it and you can easily suspend disbelief and say there's something alive here. It may not be like me, but there's something that's alive that has, intentional state and affect and so on. Okay. And again, it's trying to be easy to interface to your AI system. Okay? Any questions? Yeah.
Is it always just the red stick figures, or can you add art?
Oh, yes, you can add art. I haven't done it, but I can't think of any reason why you couldn't bring a skinned mesh in and compute the bone transforms from the positions of the particles. It seems like that would be really, really straightforward, but this is my second 3D graphics program, so I don't actually really know how skin meshes work. So it's kind of on my list of things to do to dive into the model class in XNA and, I know there's a list of matrices in there. And they correspond to the bones, and learn enough about which matrix corresponds to which bones so that I can then hand it to an undergrad and say, do it. That's the idea. Then there's a separate set of issues in terms of authoring about how you tell the system about the correspondence in the model, where to locate the particles in sort of the original, whatever the original pose of the model is when you're importing it from the FBX file. It would be nice if you could do that in an automated manner. So there is, a little bit of complexity. There's a little tool building complexity there, but in principle, it's easy. Yeah?
What about hands and feet?
In principle, easy to do. I haven't bothered to do it, but, they're just more particles and appendages. Now, in terms of...
What about getting the foot roll and all that kind of stuff? I can kind of see how you deal with particles.
So you mean getting this kind of thing...
That and,
Right. Yeah. In principle, sure. I have not studied human gait deeply enough to know whether that's something that's easy to do. In principle, here's what you do. You have a particle for the ball of the foot. The ankle is passive in the same way that the knee is, and you run the same algorithm with some additional joint constraints. What I do is I try that and see what happens, and there will probably be something about it that's suboptimal. But hopefully it would be something suboptimal that would be easy to fix. But I haven't tried doing it. Now, the thing that's hard to do would be if you want to put in hands and you really want to compute hand shapes for grasps properly. That's a hard, complicated thing, and it's painful and good luck to you. I'm not trying to do that in part just because for this kind of a system where I'm trying to not cheat on, well, for this approach, if you were to put in hands and you wanted to do real grasping, then the collision detection system would be doing a lot more work because suddenly you have a lot more cylinders that you're having to collide, and so it would just slow things down. So in this version, I haven't tried to do that.
For my applications, you could fake a lot of the shapes, actually.
Probably.
And probably get away with
Yeah.
not having to do all the calculations.
Right, and so if you really don't care about that, especially if you're putting some kind of a skin mesh on anyway, then you can just kludge the hands entirely and just, you know what direction the forearm is pointing, you can compute from that. If you know something about what you want the wrist to be doing, you can compute the transformations for the hand from that. I have to admit, I'm still personally, I'm an AI guy, so I'm still personally at the level of why is it that I reduce the number of triangles in my cylinders and my frame rate doesn't go up? Oh, there's this thing called batching. So that's the level that I'm, having to learn about. Anything else? Okay, well, I have some very high-level stuff about mammals and neurophysiology, but we're kind of short on time, so I'm not sure, if you have more questions about Twig, that might be it might be better to stick with that than to go off into the other stuff. Okay. Well, so, what is it that I'm, sort of really spending my time thinking about? I'm interested in thinking about how do we simulate personality and emotion and things like that. And partly because of my background and partly because of a bunch of other things, I'm really interested in trying to take seriously the notion that we're all just mammals. And so I want to learn about what we know about the neuroscience of sort of the general mammalian control systems, because there really is more that we have in common with other mammals, and in fact with other vertebrates, than there is that we have that's different in terms of sort of large-scale architectural stuff. Fish don't have language, but fish have hippocampuses, they have forebrains, they have thalamuses, they're called different things, but it's the same stuff. And when you give anti-anxiety drugs to fish, they actually have the same behavioral profile in fish that they have in humans. So there's a lot that's in common there, and so I'm interested in looking at that stuff. So, and it also turns out that the people in the personality and clinical psychology group at my university are heavily influenced by recent work on neurophysiology. So my basic claim is if you look at what the architecture of that system is, it's pretty quirky. It's not what you would design as an engineer, but it's kind of interesting. It's what you get when you evolve something simple and then you evolve additional layers of complexity on top of it. The quirks that you get from it actually manifest in interesting ways in human behavior and are important in the failure modes of human behavior, and so I would argue are relevant to narrative. So a lot of this takes place in the context of what are called dual process theories of human motivation, which are pretty common. And here's the basic idea. From 10,000 feet, your behavior behaves very much like you have two systems, an impulsive system that is just trying to approach good stuff and stay away from bad stuff, and then an effortful control system that can reach in and override that. Okay? And so the impulsive system is sometimes called the Homer Simpson brain. It's the system that says, donut. It's the system, so that's the approach side. It's also the system that says, I don't want to do my homework. And then the effortful control system is the system that's on top of it that reaches in and overrides them and says, no, you have to do your homework, or no, you shouldn't eat that donut because you already ate 5 of them. Now, why is it you think that there's 2 separate systems for this? Well, the answer, there's a bunch of evidence for that. Partly it has to do with when you get lesions in certain parts of the brain, one part or the other part of the system stops operating. But also the effectiveness, in particular the effortful control system, varies a great deal with age. It keeps developing up through age 25. But also there are drugs that can selectively improve or worsen the effectiveness of this system. So if you take Ritalin or Adderall, a lot of what that's doing is it's making this system better able to override these systems. And Carver et al.'s argument is that that's actually part of what SSRIs are doing for treating major depression. But conversely, if you take ethanol, i.e. beer, that's reducing the effectiveness of this system. And the thing that's really cool is there's this great literature, and it's a very, very well-documented phenomenon, that the effectiveness of this system goes down temporarily with use. The specific argument is it acts like a muscle. When you use it too much, it gets tired out and it doesn't work as well, and there's a refractory period. And so here's the argument behind it. Here's an example of the phenomenon. The way we're going to assess your ability to do effortful control is we give you a cryptarithmetic puzzle, and we don't tell you that it's unsolvable, and we time how long you stick with it before you give up. Okay, and now here are the 2 subject conditions. One of them, I give you the one of them, you walk into a room, there's a plate with, quote unquote, a yummy cookie, that's an actual quotation from the paper, and the other has a Snickers bar. And I say, eat the Snickers bar, you eat it, and then you do the cryptarithmetic puzzle. That's the control condition. The experimental condition is you walk in, you see the same stuff, and I say, eat one of them. And so you actually have to choose which one you do. Forcing yourself to make the choice between the cookie and the Snickers bar measurably reduces your performance on the cryptarithmetic puzzle. Yeah?
So that would argue for optimizing your stressful choices. For instance, you wouldn't want to break up with your girlfriend right before taking a test.
Exactly. And so it has all kinds of interesting implications for things like addiction, the obesity epidemic. You know, why is it that people are eating more? Well, partly there's higher availability of high-calorie foods, but also the average length of the work week has gone way up, and just in general, the level of stress that people are under has gone way up. And so consequently, when you get back from work at the end of the day, you don't have the energy to override this. Okay, sorry, I went on a digression here. Here's the system that, the data on this is still at a pretty hand-wavy stage. But if you zoom in and focus on the impulsive system, we actually at this point have very good neuroscience on what the impulsive system looks like internally. And so you've got an approach system, you've got an avoidance system, and the really cool thing, and this is what all the people in the clinical and personality psych group in my department are into, is you have a third system, which is roughly the hippocampus, which is a conflict detector. And it notices when there are conflicts, and in particular when there's a conflict between wanting to approach something and wanting to avoid it. And when that happens, it reaches down, it inhibits both sides, it increases like autonomic arousal and so on. It also triggers a whole set of information gathering behavior. So in other words, you go into a risk-averse mode and you start trying to gather more information. So you get increased memory scanning, you get increased environmental scanning, and so forth. And here's the argument. If you look at brain lesion studies, and if you look at the effects of anxiolytic drugs, drugs that cut anxiety, and panicolytic drugs, drugs that cut panic. Panicolytic drugs affect this and not that. Anxiolytic drugs affect this and not that. And affect, in particular, the behaviors associated with these things. Similarly, the neuroscience, the lesion studies. And so basically, fear and panic are the avoidance system. Anxiety is actually, in some sense, anxiety is a separate emotion that corresponds to distinct behaviors that can be modulated independently. And then that becomes interesting to the psychologists because the personality people like it, because you can tie important personality traits, in particular the big two, extroversion and neuroticism. Extroversion roughly coincides to the gain on the approach system. Neuroticism roughly corresponds to the gain on the avoidance system. If you do the actual studies, what they really correspond to is sensitivity to cues for reward and sensitivity to cues for punishment, which means a 30-degree rotation of the extroversion and neuroticism axes. Anyway, so we're working on simulating this kind of thing, and they actually, I'm out of time. There's actually some wonderful stuff they have now on the distinct behavioral systems involved in different kinds of avoidance. There's actually a whole series of parallel avoidance systems that essentially make a hierarchy of stupid and fast to smart and slow. They're all trying to do roughly the same thing. And so you can actually plot out the time course of something like a startle response in terms of the startle happens 10 milliseconds, or the stimulus happens 10 milliseconds later, the startle system engages, and you get all sorts of stuff like you might not know that you blink when you're startled. You hold your breath briefly when you're startled. But that's 10 milliseconds, which is incredibly fast. And then maybe 100 milliseconds later or so, then the actual behavioral systems kick in. And first you get high-intensity freezing. All of the motor outputs of everything get shut down for a brief period of time. That's what flashbang grenades are relying on in part. Although they're relying on other effects too. And then later on, first you get the undirected escape system because it's fast and stupid. And it's either, depending on its assessment, either trying to attack the thing that startled you or just get away from it, but it's doing it in a very sort of haphazard manner, and that's why you're as likely to bump into something when you're startled as to actually move away from it. And then much later, the higher level systems kick in, tell those lower level stupid systems, okay, shut up now, I know what to do, and have you do other stuff. We're at the point now where we actually know enough about this so that it's really kind of plausible to simulate it at a kind of a qualitative level. I'm not interested in doing like accurate reproduction of neuron spikes or anything like that. But in terms of the macro architecture, we actually know enough about it that we could simulate it, and it's simple enough that you could really put it in characters, and it's not going to require enormous amounts of CPU time. But at least potentially, it can give us sort of some compelling performance in our characters because you're going to get sort of nice timing of everything. So that's the idea. That's what we're working on now. Okay. Thank you. Any other questions?